Okay, is my screen visible to everyone?
Yes, sir, it's visible.
Yeah. Okay, then we'll start. Okay. So last week we have done the programming for the what you called adder. Okay. So today we'll do the programming for first 4-bit adder. Then so today's agenda is first we will finish 4-bit adder. Then we'll do the flip flop. Then we'll do the counter, and then we'll go to the Wallace multiplier. Carry look ahead adder you may design using the 4-bit adders technique. So I will basically tell you how to do a structural programming today. So the whole session will be related to how to do a structural programming, how to write the flip-flops, how to write the counters, what will be the differences between these, and how to synthesize and check the results. What is exactly expected from all these projects. Uh, so we'll look into it. So we'll start the session. So first, I will show you and if at the end time permits, I will finish the carry look ahead adder also. Okay, because Wallace tree will take a lot of time for understanding as well as programming. So first, I will show you what we have done last week. So I hope everyone is having this program, adder program. I hope everyone got this last program. Okay, is everybody having this program? Please tell me. All
Yes,
of
sir.
you must be, yeah.
Yes, sir.
Okay. So we will start a new program. So let's see. Yes, streaming started. Okay. Okay. So look at this full adder.v. So now we wanted to create a 4-bit adder. So I will make something like this, a code. Okay. So write down here bit for adder in the same uh, project. So open the previous project. In the same project, we have to write a new code, which will include the previous adder. Okay. So I'm writing bit for adder. So if you are doing particular coding from once, you just have to keep the same project. You don't have to change the project until and unless your design is changed completely. So next, I want inputs A in, comma B in of size 4-bit. Okay, I write here comma. It is dot. Let's see. C in of 1-bit only, and sum is the output of size 3 down to 0, and carry is 1-bit. Next, finish. So please finish this part up so we can start the next part. I hope now everyone is okay with the Xilinx. Everyone has installed the Xilinx. I have not floated the assignment because many people were facing problem with installation and they were not able to cope up with many things. So I have not floated first assignment up till now. But today I will float all the assignments. All assignments will be on by today. People need time for this workshop. So because I am getting many queries from many people. So please finish this. Are you all done with this? Once you finish, please tell me. So we have to create bit4 adder module. Later I will tell you how to make this program generic. What do you mean by generic? We'll see. So in this program, we'll see all these things. So why HDL is popular, you will come to know after that program. Please make this program in the same project which we made earlier. If you have not made full adder, quickly make a full adder or download it from the resource I have provided. The resource is available on the site. You may use that as a reference. Okay. Is it done? Shall we move ahead? Please tell me. Shall I move ahead? Are you all done with this program? This part? Please tell me if you are done with this. Are you all done with this? Shall I move ahead? Please tell me. Or I have to show the procedure again. Okay.
No, sir, we can go ahead.
Okay. Okay. Please tell me. So otherwise, there will not be any understanding. Okay. Now we wanted, what we have to do is we wanted to design a 4-bit adder. So please look at this section. What we have to do is I will start the Google Jamboard so I can explain what exactly we wanted to do. Till then, you all please finish your basic code. So if anybody is not done with the code, they will finish the basic code. So we have to create a 4-bit adder. So let's see what we have to do. Okay. What we have to do is we have to create a 4-bit adder. So as I said, we should design everything before programming. So before starting the program, we'll design. Okay. So I have inputs like this. So this is A, which is 3 down to 0. And this is B, which is 3 down to 0. And there is C. This is C in. Okay. Now I have inside 4 full adders. I wanted to instantiate 4 full adders like this. So the 4 full adders will be like this. Now what happens? This A and B, I will write something like this. Basically, these are the inputs. So these will be like this. This is A, B, 4 inputs. Okay, so this is A0, B0, and this is A3, B3. Okay, this is A3, B3, and this is C in. So that C in will be something like this. So C in is coming from this side. Okay, and this is a passing carry. Now you can see the ports will be like this. This is output. This is carry. This is the last carry. This is output. Okay, and these are the sums as we generally design. Okay. So this is S, sorry, S0, S1, S2, S3, or I can call it as a sum 0, sum 1, sum 2, sum 3. Okay, so this is sum 0, 1, 2, 3, and this is carry. And here I am sending input. So now this is full adder. Each and every full adder is there. So this is FA. I want 4 instantiations. So I will create 4 instantiations, and with these 4 instantiations, I will be having, so there will be 4 instantiations, and with these 4 instantiations, these will be the inputs which I already developed, and these are the internal signals. So this is wire. Okay, so I can call it as a carry wire or a C wire. So this is C1, C2, and C3. 3 signals we wanted, and there will be one output. Okay, so C1, C2, C3, these will be the wires we wanted, and carry will be the output we wanted to create. So that's it. This is what we have to do. Simple. So let's do it. So I will create one wire. So how to create a wire? Write like this. Wire C1, C2, C3. That's it. 3 wires we needed. And then instantiation. Instantiation, how to do it? Like, write something like this. Adder DUT1. So this is entity, the entity name. Here it is called as an entity. So I am calling this function. So this name and this name, these two must match. Then and then only the function will be called. So that means this module will be called when this name is matched. So generally in C, C++ programming, we call the module or a function by name. In the same way, here we are calling the module by name. Now we wanted to map the ports. Okay, so mapping the ports, what is the method? The idea is simple. For mapping the inputs, what I have to do is I have to map A in 0 to A in, B in 0 to B in, C in 0 to C in. Okay, so first I will write something like this. In 0, comma, C. Here the importance is to the position. So instead of A in, if I write here B in, then B in will be mapped to the A in and A in will be mapped to the B in. Okay, so if I write here B in, then what happens is for the input A in the full adder, there it will take for input in the full adder, it will take uh, B in instead of A in. So importance here is given to the position where you are writing the input. Okay, so this is called as a positional mapping. There is a associative mapping also. You can specifically mention which port is mapped to which. So B in, then I'm writing C in, then see, this is how you can write. So I'm accessing the zeroth input of A in, zeroth input of B in, and C in is the carry in, and mapping it to some 0 as we have done, and carry. So here you can't write carry, so you may write C1. See this. The output is C1. So I will make change here. Watch this. A0, B0. As is in the same way I will write. So there will not be any difference. There will not be any difference and no confusion will be there. So I will write here. So A0, A in, 0, and this is B in 0. So that I can write here. What happened here? Okay, B in 0. So this is A in 0, B in 0, and this is some 0. In the same way, we can manage the remaining part. So just copy paste it. Control C, Control V, Control V, and Control V 4 times. Now this is A in 1, A in 2, A in 3. Then B in 1, B in 2, B in 3. Then C in की जगह अभी यहाँ क्या आएगा? Here you have to write C1. Then here you have to write, it will become C2 and this become sum 1. Then you have to write here C2, then C3. So in the same way, you have to go ahead. See what I'm doing here. See this C1 is the output was the first full adder, which is given as an input to the next full adder. So C1 will become an input. This C1 will become an input for the next full adder. So instead of a C in, I'm writing C1. So this C1 is mapped here. C2 is mapped here. C3 will go here. And the last output, this. You can see this. So this is up to this, I can write A in 3 and B in 3. Okay. So this is A in 3, B in 3. And this is sum 3. And this is carry. So C1, C2, C3 we already mapped. So the last here I will write carry. Done. Okay. So you can see this. Now I can make it as a top module. Hello? Yeah. So this is done. Now synthesize. Let's see whether it gets synthesized or not. So everybody please finish up to this point. I will wait for 5 minutes. Is there any query? There is some error. We'll see what is the error. Okay, I have written the same label to everything. So this is a label. The label should be different. So create a multiple labels. Here there will be problem 2 and 3. Sorry, 3. Please finish it quickly. Okay. Rerun. Otherwise, there will be multiple driver. Multiple driver means one signal is forced by two different inputs. That is called multiple driver, which is not in the allowed in the hardware. Reason being, if you uh, force one output from two inputs, the result will be ambiguity. See that it is successful. So we can see the RTL schematic. The RTL will look like something this. Okay, look at this. The RTL will be something like this. So this is our paper pen method. If you can see this. One full adder, it is looped. Again and again it is used. Okay. So this is a full adder. It is a bit you can see. Now, when you see the technology schematic, you will come to know the exact kind of structure is created. See this. So total 8 lookup tables used. 4 for carry, 4 for the sum. So total 8 lookup tables. If you can see the summary reports, you will come to know. Total number of lookup tables 8 and the slices are 4. Why? Because in one slice there will be 2 lookup tables. So that's why total number of lookup tables 8 and the total number of slices will be 4. So total 1408 lookup tables are there. From that we have used 8. So is it clear? Everybody please tell me. So we can simulate this code. Once you finish with this, please finish it quickly with 4 adder. Are you all done with this?
Yes, sir.
So now we can move ahead for the test bench. Okay, let's see the test bench for this. Okay, Verilog test bench. So I will write bit bit for adder PG. Give a proper name to all the files. I suggest most of the time give relevant names because it won't create problem when you debug the thing. There will not be problem until and unless there is a bug. Once there is a bug, you see waveform, then you see code again. So just looking at the name, you will be able to find out from which module this signal is coming. So give such kind of names, relevant naming. It will help a lot in a programming. Many times people do not follow the naming conventions, and that creates more problems while uh, handling all this. Okay, so now we are creating a simple test bench. So what you have to do is you just have to add a simple code at always add. You may finish this part. Till then I will copy directly the test bench. I have written already. have a written test bin for my code. I already written most of the codes. I will share all these codes with all of you. So I have written the same way code. I can show you. Simple technique I have used to do the thing. You can see. I use the same method the previous time used. The only thing is that here instead of doing the negation, I am adding +1. So every 5 seconds, scene will be toggled. Every 10 seconds, A in will be toggled. Every 160 seconds, B in will be toggled. The same logic. Not toggled, incremented. A and B will be incremented, C will be toggled. So every 5 seconds, C is toggling and A and B are incremented 10 and 60 nanoseconds respectively. After 60 and nanoseconds respectively. Okay. You can see this now. We can simulate this code. Bit 4 adder. Let's simulate. Let's see what we get. There is some error. Okay. Did I add the code mistakenly? Files. There are 2 files already in the simulation. So that is creating the problem. I will remove this file. One of the file I have to remove. So I will remove this file. Okay. Now we will simulate. Then I will tell you how to make this code generic and why generic is needed. That is more important in the programming. These are very basic part right now we are learning. Okay, watch this now. So now, please everybody concentrate on the screen. How to test these things? Because now this is very large. How are you going to test this? Until and unless you become a very good, very proficient programmer, it is very difficult to test these kind of things. Uh, After you understand programming, you will be able to write a logic in the code itself to test it. So how to do that? That obviously require a lot of practice. So I'm not going into those things. The simple thing you can do is go there and click on the right click and make radix to unsigned decimal. Just select the signals and make right click and make it unsigned decimal. Okay. Once you make it unsigned decimal, what you have to do is you have to track signal which is changing continuously. That is C. So look at this. I'm tracking C. After every 5 nanosecond, it is changing. Okay. So 0 plus 0 plus 0 is 0. 0 plus 1 is 1. 1 plus 1 is 2. 2 plus 1 is 3. In the same way, we can go here. See this. 14 plus 2. 14 plus 2, which is 16, which is nothing but 1 and 0. All zeros. You can see this. 1 and zeros. That means 16. Because this carry is 1. So here you can see this 1 0 0 0 is 16. Okay. Then again 0 plus 3 is 4. You can see here 0 plus 3 is 3. Okay. Because this is 3 and this is 0. 3. Then 3 plus 1 is 4. See this. 1 plus 3 is 4. This is 0. Then 1 plus 3 plus 1 is 5. So in that way you can test. Or there is another way, you can make all these on and you will be able to check it. There are many constructs in the Verilog which will help you to find out uh, how to test the internal signals if anything goes wrong. Another thing you can do is if you wanted to see the internal signals of the modules, that is also possible in the simulation. What you have to do is on the left hand side you can see the bit adder TB. Under that, click on UUT. um, um, Under UUT you will find the multiple signals. So you what you can do is you can say add all these signals. See, UUT has multiple signals, so you can call add this signal. If you click on UUT, you can see the input signals of the UUT, and you can, let's say मुझे C1 C2 C3 के results देखने हैं, so I will make it add to waveform and I will restart the simulation. Here, restart the simulation and simulate. See this. Now I can see the C1, C2, C3 also. So it is possible to see C1, C2, C3 also, the internal signals of the modules, which are not visible in the hardware. Please remember, these C1, C2, C3 are not visible in the module. There is a utility in the Verilog test bench also called as a hierarchical operators. These hierarchical operators bring internal signals from the module to the test bench, but that takes hardware if you put it into the actual programming. But this, if you do in simulation, there will not be any hardware. So basically this is a viewing utility only. So hierarchical operators also you can use, or this is a simple method. You can directly take the signals from the DU UUT and put it into the waveform and you can check the results. Okay. So I hope up to this point everything is clear. Is there any question? If you have any question, please ask. I'll wait for 5 minutes, and if you have any questions, I will answer that question. In the next section, I'm going to start Wallace multiplier. So up to this session, everything will be remaining to the basic. We'll stick to the basics. Are you all done with this? Please tell me. Everyone, are you all finished with this programming? Now the question is, if I wanted to make this as a 32-bit adder, how can we do it? Is it possible to make it as a 32-bit adder or a 16-bit adder or a 8-bit adder? See, if I wanted to write 8-bit adder, I have to change the complete code. ये इसको उठाना पड़ेगा, फिर से add करना पड़ेगा, modify करना पड़ेगा. That I have to do. Is there an alternative for this?
We can
So
use
that,
this as a submodule for it for a 32-bit because this is
yeah,
a
that is
4-bit.
another solution. But if I wanted to make a modification in the same code, how to do it? See, many time what happens is we have lots of design. Let's say I have wanted to instantiate 100 modules. So is it advisable to write 100 modules, because it will be a very difficult task, because I have to copy this again and again, again and again, 100 times, then more, check the inputs, which will be a very tedious task. It takes time, as well as it consumes a lot of energy to check each and everything. The solution is called as a generic programming. You can use and generate multiple instances on the same time. How to do it? See this parameter. There is utility called as a parameter. You may write this as a width is equal to 4. Okay, you may write something like this. So for doing this, what you have to do is you have to make a small change into the circuit. Okay, I will make a new program. So I will keep this program as it is. I will create a new program and I will tell you how to do it. Okay, I will write a new source, Verilog module. Then here I will write generic adder. The test bench will remain same. Test bench will not change. कोई फर्क नहीं पड़ेगा test bench पे. I am just changing the input. What I am doing, I'll show you. Okay, I'm writing A in, B in, C in, sum, carry. But I am not giving any width for all of this. Okay, so I am not putting a width, or I can put up a width if I want to. So I will make it 3 down to 0 currently. So later I can modify it and I can make it 3 down to 0 and next finish. So you may write your own code also if you want. See what I am doing here now. Please check. A, B in. Okay. C in, then sum
So
and
B is
carry.
missing. B is
Yeah,
missing.
yeah, yeah. B in, I'm writing B in, C in, sum, carry. Okay. Now this is first I'm declaring input here. Only inputs are declared, but its width not declared in the declaration. See the change in the code. Okay. Parameter width is equal to 4. Okay. I will write it as a equals to 4 semicolon, and I will make this change as width minus 1 down to 0. Okay. Then I will make a small change. Input C in, that is 1 bit input only. Then carry will be output, and this will be output carry, and I am making this as a width minus 1 down to 0. So that's it. Now what happens? See this. What is the change in the code? Now whatever the parameter I will change, accordingly the width will change. Now the same program we have to change also. We have to make the changes in the program also. So now I wanted a wire. I don't know how much is the length of the wire. So wire inter sig. That means I am saying intermediate sig, or I will write CA sig. That means carry sig. I don't know the width, so I will write here right now. जितना भी width होगा उससे एक कम. Whatever is the width less than that, one less than that. That much is I have to do. Okay. So I will write here, or I can write directly width down to 0. Same width का बनाओ, कोई प्रॉब्लम नहीं है. एक हाथ सिग्नल ज्यादा हुआ तो बाद में डिलीट कर सकते हैं हम लोग. So I am writing here wire sig. Now what I have to write? I have to write a statement called generic. Now this is the biggest tip you can remember for your Verilog programming. Every time it is not needed to remember the Verilog syntax. In fact, I do not remember any of the syntaxes. I am coding, but I do not remember any of the syntax. I can't. It is very difficult to remember the syntax. And please note down, students, teachers, syntax doesn't matter. The reason is nowadays the tools are so smart that they can create the syntax. You have to write a logic. So more importance is given nowadays to writing a logic, not to writing a syntax. Why I am saying that? See this. I will show you. The Xilinx itself creates a utility and it helps. So click on this bulb. If you click on the bulb, you can see the codes, Verilog. So in that I am clicking on the Verilog. In that I have to click on the synthesis constructs. You can see all the syntaxes are shown. This is a syntax. You just have to make change in the code. See this. Simple flop. Everything is written. each and everything. If you do these codings also, you will be an expert programmer. You just have to see what code I wanted to write. Just copy it, change the names, and done. Only thing you have to do is you have to change the name. So right now I wanted to write a code for a generate, and I wanted to write a simple generate code. So I wanted a multiple instance. So I will take as it is. Okay. So I will show you how to do it. I'm copying this generate code. Okay. I have copied it. Just for understanding purpose, I'm using it. See this genvar. So genvar, it will create a variable. So I will create a variable j. The way you write in a C coding, you just have to write in the same way. J is equal to 0, j smaller than width. लिमिट कितना है हमारा, width तक जाना है. Then j is equal to j plus 1. That's it. So this is a for loop which will move from j is equal to 0 to width. Whatever will be the length of the width, accordingly it will move. Then begin given label. So I am writing create adder, or I can write adder gen, or whatever name you wanted to give. Now, instantiation. What to do in instantiation? I have to write the same code. Just copy this code from here to here. Simple. Nothing changed. Instead of writing this, I can write here J. Here I can write J. Instead of writing C in, what I have to write? I have to write CA sig J and some J and CA sig J plus 1. That means next instance. Okay, that's it. Then now advantage. Here one thing I have to change again. I have to write here assign CA sig 0 is equal to C in, because input I have to assign to the 0th bit of the wire, because now C in is not visible in this. So I have to mark this C in here to CA60. See what happened. Now CA6 J plus 1. And last statement I have to write after completion of the generate. Assign carry equals to CA sig what? This is 0, this is 1, sorry, 0, 1, 2, 3, 4. So that means fourth. So I have taken a correct length, width minus 0, 4 down to 0, 1 extra. That's it. Done. Now see this. You can see under generic adder, there will be one utility, one DUT only, which is called again adder. Okay. So is this code understood? Is there any question? Now, what is the advantage?
Sir, at the end that you have given CASIC 4,
Hmm.
will you come to know that 4 has to begin because
What, madam?
width is variable, na? So how will
Yes,
you come to know CS signal 4 has to be given to carry?
because that is the last width, na? ये वाला है. So you can write here width instead of that.
Acha, acha. Instead of that, can we take width as an input, sir, from the user?
No, we can't take, because it will not change the other inputs, na?
Okay.
I have to change the width of A in B in also generically. So
Okay.
it is like a dynamic variable which you are changing, and everything is changing
Okay.
inside. If I make it as an input, I can't use it as a length for another input because it is a port. Once you make it as a port, it won't work. Okay, I will make it as a top module and I will synthesize it. Let's see, will it work or not? There might be error, we'll solve it. Or there might not be any error. Let's see what happens. See, now done. I have done RTL schematic series, A in, B in. So the same kind of code is generated. You can see last time also the same thing is generated, right? Then RTL schematic, let's see the RTL schematic. See, the same RTL schematic is generated. Although I have written a different code. Okay, now what is the difference we'll see? For that, first we'll see the report. How many? 4 slices, 8 lookup tables. Remember this, 4 slices, 8 lookup tables. Now what I will do is, I will make the parameter as 8. Let's make the parameter 8 and synthesize it again. So I have changed the parameter to 8. Will it work? First, I have written a simple code for which I am changing the width and everything will change. So now the code is generic. Multiple instances will be generated depending upon the parameter. Let's see whether it is happening or not. So see this, now it becomes 7 down to 0. If I click on this, see this. The hardware remains the same, RTL hardware, only the length is changed. But now see the technology schematic. The technology schematic is completely changed because this is series. Now 16 lookup tables are used. You can see this in the design summary. See this, number of slices 9 and 4 lookup tables 16. So total 16 lookup tables used. In the same way, you can make it to 32, it will work. You may try. Is there any question now? Everyone understood what I did? And please try to use this utility. If you are not able to code very quickly, use it. In the VHDL also, you can write UCFs also. See this, a specific UCF for FPGA is also given. You can find it out. Configuration module, devices. So everything is given. You just have to go and check what is given in the help. So this help is freely available. You may use it directly. Okay. You can remove the language. So done. Have you all understood the logic behind it? Please tell me. If you have any question, please ask. We'll talk about it. If you got any question. Have you all understood how I did the generic coding?
Yes, sir.
So this will be very helpful when you are doing the projects. You don't have to write a multiple modules. The general tendency is people write lot of codes, lot of adders, lot of full adders, half adders. So multiple modules will be there. So when you go and debug it, it is very difficult to debug. This will be very easy to handle, as well as you can scale the module very easily. Very helpful for scaling the design. So I can scale it directly to 32-bit, just changing the width value to the 32. So if I change it to 32, the module will be 32-bit generic adder. So this coding is very much popular in the industries, and industries do wanted to use these type of codings. So very popular type of coding. I hope it is clear now. Are you all done with this? So just I will wait for 5 minutes, then we'll go to the next module. Please finish it. Then we'll go to the simple coding, that is a D-latch. I'll wait for 5 minutes. If you want to finish the code, then I will start again. Please finish it quickly. Okay, everyone done? Shall we go to the next module? Okay, now we'll go to, shall we download it? If you want to download it, you have to do some kind of coding like this. So this is a, okay, just a minute. I will show you the, I have downloaded also this code onto the board. So if you want to download it, you may use this kind of a UCF file. So this is a UCF which you can use. You can see sum 0, 1, 2, 3 carry and LED 5, 6, 7 which you can use. Multiple LEDs you can use and one carry you may use. So this is not required actually, only 5 this is required. So sum 0, 1, 2, 3. So pin 46, 7, 48, 49, and 50. And for the inputs, you may use this. See this. A in 0, A in 1, A in 2, A in 3. So 68, 69, 70, and 64th pin, and 58, 59, 60, 63rd pin for B0 to B in. And for C0, C in, you may use 80. So these will be switches. One switch I am taking from the push button. So this is a push button switch. You may try. So you may just synthesize that and it will work. Bit 4 adder. So right now this is written for the bit 4 adder. Set as stop module and it will work for bit 4 adder. Okay, so shall we go ahead? I hope everyone has done up to this generic programming, generic coding technique. Then I will start the latches and flip-flop. Okay, wait a minute. I will start with the latches and flip-flop. Okay, now start new source. We will write latch. We will write something like this, latch. Verilog module. Next, I will be having input clock, enable as an input, and D out as output. Next, and finish. So you may try this. I'm creating a new latch called as a clock, enable, D out, and finish. Okay, so whoever is not knowing what is difference between the latch and flop, please remember the latches are level triggered and the flip flops are edge triggered. Okay, so generally if you see the simple code, I can tell you the simple thing. So if this is the clock, this is the clock. So whoever is not knowing, whoever knowing, there is no need to understand new things. So it is just a repetition for them. Clock, and if it is a data, something like this. Okay. So now I am writing a positive edge triggered clock. So these are all positive edges of a clock. Okay. So these are positive edges. So the clock will trigger only on these edges. Sorry, the design will trigger only on these edges. For the flop, for the flop. So this is a positive edge. This is data. Okay, that is input data. Now, when I'm taking the output for the clock, whatever data is there on the edge, that will be sampled. So here 0 is there, so 0 will be sampled. Up to this, the result will be 0. Here it will change the position. because data is 1 here. So it will go to 1 and it will again come back here to 0 because here the result is 0. Now see the difference. Here there is a switch happened in between in this clock, but that is not taken. It will take only the change which is happened onto the edge. So it will go down up to this point and again it will switch back to 1 like this, and it will remain 1 up to this point, and then there will not be any change. See this is flop. So this is output for the flip-flop. Now what happens in case of the latch? So in case of a latch checks the this level. इसको check करेगा latch. This is for latch. Okay. So latch is checking levels. These levels. So I can write here latch. This is for flop. Okay. Now see this. At the start, there will not be any change for the latch also, but at this point, it is changing. So this change will be accepted by the latch, but not by the flop. Okay. The flop is not changing, but latch is changing. Again, it will change at this point, as this is on the positive edge, positive level, sorry, and then it will go up to this point. See this, here it got down, so यहाँ से ये change यहाँ तक जाएगा up to this point. Again this change is taken and this change will be maintained up to this point. Although here there is a change, here there is a change, there is no change, but here this change is not taken, but latch has taken. Here this change is kept as it is by the flop. Okay, see this, ये यहाँ तक ये वाला change और ये वाला change flop ने लिया ही नहीं है, जबकि latch ने लिया. Latch has taken this change. Okay, now it will go up to this point and then it will be down. So this is different between the flip-flop and latch. So please remember this change. You have to understand this change for understanding the flop and latch. I hope everyone know this. There is no more explanation needed for this. Okay. So we'll see how to write a flip-flop and latch. Let's see our template. Will it help us? I can show you every time this template if you want. So I'm writing latch right now. So let's see, flip-flops में latch लिखा हुआ है क्या? No, they have not written the latch. Is there anywhere they have written the latch? Sometimes they write, sometimes they don't write few things. So latch is not written, I guess. Generally, we expect simple latch to be written here. No, they have not written the latch. Flip-flops are written, but latches are not written. Okay, latch is not written. So we will write. Anyways, I have code written. I will show you the code. I will not write each and every code. I will explain all these codes to all of you, how to do a coding and everything. Okay. So I'm trying to create a D latch with positive edge and negative reset. Okay. So let's see what is there written. So I will first copy this and then we'll talk about it. Or I will write a fresh code here anyways. I'm not using reset, so I will directly use the enable instead of anything. So I will write something like this. Always at shit. I have not saved the code, I guess, mistakenly. You want Mazza? Yes. Okay. So I mistakenly made a change. Okay. Sorry. So I will write here. Okay, this is called the always block. Okay, always block. Up till now, whatever block we have seen, all those are parallel programming. Here we have seen the parallel programming. All these statements are executing concurrently on the same time. Everything is getting executed parallelly. That means all adders are getting executed parallelly. But in this case, the statements will get executed sequentially as happens in the C programming. The same kind of program we can write here. What we have to do is here, see this, there is one more thing we have to do. We have to write something like this, register D out. That means here output we have to register. So generally we write something like this, register, or you can write here also register if you want something like that. That is also allowed, but I am specifically writing register D out. Okay, always at clock, then enable. So that means it will trigger at clock and enable. And I will write if enable, then if enable, then simple write D out is equal to D in. I have not taken input. So I will mark here one more input as D in, which is missing there. Or a data, you can call this as a data. Okay. So D in and D out. And here I will write end, and end module is already there. That's it. Simple. Yeah, I have to write semicolon. Okay, that's it. I hope now everything is okay. What happened? Output D out. Syntax error. Yes. Here we need input lock enable D in. What's got wrong here? Okay. I have to write something in a different way. Nothing wrong is written. What is the error? Error can open. Error is here.
सर सेमीकोलन पाहिजे का? डी आउट इज इक्वल टू डी इन.
तिथे
28
तर
लाईन
पाहिजे
नंबर.
सर, पण तो एरर वरती दाखवतोय, मी ते बघतोय की
ओके ओके.
वरती काय
हां
एरर
हां
आहे.
हां हां.
हा एरर काय ते मला कळलेलं नाही अजून. देर इज वन एरर हिअर which is I'm not understanding. Actually, that is probably यहाँ semicolon नहीं, यहाँ comma चाहिए, because there are multiple ports.
हां, लास्ट लाईनला बरोबर. हां,
Yeah,
डी इनच्या 22 नंबर लाईनला कॉमा लास्टला सेमीकोलन.
yeah, yeah. तिथे पण comma पाहिजे, and probably it will work. Yeah. Now it should work, I guess. Why it is there? ये सब जगह चल रहा है, ये क्यों नहीं चल रहा है? Okay, it will work. Int okay. Okay, now it will work. So this is simple. So look at this. For always clock and enable. Why I'm writing clock and enable in the bracket? It means if enable and clock, if there is a change on clock or enable, the data will change. Here I have to write D in also. That means these are sensitive to the clock. Or you may write something like this. Generally, I get confused with the syntax of VHDL. Clock or enable or DIN. इसमें से किसी पे भी change होता है तो output will be changed. So all these are sensitive to the data. That's what it means. That's it. And we can synthesize. You may synthesize it. Okay. Let's see the RTL code. Okay, sorry, mistakenly I synthesized the previous one. Set as stop module and it will work. Let's synthesize. Error, redeclaration of D out. So I have to write here rich. Redeclaration is not allowed. Okay, see this, there is no error, but warning. What is warning? Input clock is never used. This port will be preserved or left unconnected with top level value. Found 1-bit latch for a signal D out. See this. Here clock is actually not useful because I am using enable, and that's why there is no use of a clock. So I can remove the clock, or I can mark it as a enable. That is correct actually. So this is simple change I can do, and that will work. Now it will be a latch. Actually, I used enable or a clock. See here the change is happening on the level. That's why we used enable, but there is no need to use. So found 1-bit latch for a signal D out. So it is showing a warning. So generally in the Xilinx, you can find there will be a warning in the message if mistakenly latch is formed. So whenever you actually create a latch, then also there will be a warning. This is a latch, you can see. And RTL schematic, check it. So this is RTL schematic. So this is LD. Look up latch, and this is BUFG. We will see the design summary report also. You can see there will be 0 slices used and 3 bounded LABs as latch is by default created. So no actual hardware is taken, but there is a formation of a latch. You can simulate it also and you can check. Okay, first ये complete करो, मैं आपको latch का program simulate करके दिखाता हूँ. Just finish it, then we'll go to the flip-flop and counter. We have to finish it very quickly, and then we'll take a break, and then we'll come back and start Wallace tree. So basically 25th pre-recorded session I have not given. So I'm covering all those things in today's session. Instead of a pre-recorded session, you can watch this session, and latch, flip-flop, counter, everything will be covered. In fact, I have covered up the generic programming also. I hope everyone is clear with this. Now we have to write a test bench for it. You may write a simple test bench for it. And if you are doing coding with all of you, if you are doing coding, that's very good. अगर आपका coding चल रहा है साथ में तो try to do coding. It will be very helpful, because this session will be useful when you do the coding. Actual coding is needed in all these sessions. Okay. So there is another way you can write this thing. We can add reset also if you want. So I will write reset, and I will say here or reset, and I can write something like this. If not of reset, then d out equals to 1.b 0, else if d out is equal to d in. That's what I have written here. N. So what happens here now? Reset is added. So if reset is 1, reset will be having a higher priority than the enable. So if reset is 1, d out will be 0, else d out will be 1. That's it. So you can see, synthesize it and check. You may check it. I'll give 2 minutes time, then I will write a test bench. Is there any question? Is there any question? Please tell me if you have any question. There was mistake because I have not put down a. So there is a change in. So now you can see there is a clock D in reset. Clear signal is used, and technology schematic you can see there is one clear signal added through 2 inverters. Internally ratch is taken, so mostly there will not be any hardware. One slice is added now. Now lookup table is there because of the clear signal. Otherwise there will not be any hardware. So I hope everyone understood this. So I will go to the next part, that is writing a test bench for it. So VH Verilog fixed register for it. So I will write latch TB. Next, now I have to select latch, next, and finish. See, the test bench will be similar. There will be register, clock, D in, reset, wire D out. I have initialized the entity. Starting clock is equal to like this, and write only one statement. Always #5 clock is equal to not of clock. That's it. And simple, you can write reset is equal to 0 for 100. 100 के बाद ये reset change हो जाएगा. Okay. Okay, let's see what happens. Reset equals to because it is a active low reset. So only I am giving input. Data is 0 right now. I have not given any data which can be given. Okay. So this simple program I can use as a reference, and simple thing we can do. I can write something like 25. After that, data is changing, and here I can make that simple change. That's it. Enough for us. I hope it will work now. Failed. Why there is an error? Clock is unknown type. Why unknown type? Was the data D in here? D in. Is there any error? Not of clock. Okay, look at the simulation. You may check the simulation. You can see here there will not be any change as reset is 0 up to this point. After that, data is changed. Whenever the data is changed, that output is shifted. Here you can see. Every how many seconds it is changing. Check. This is 50 to 75. 25. I have given time 25. But here the data was not accepted here because clock signal is not 1 at that time. So why this change is not taken? Because reset is 1. Okay, up to this point reset was 0. So that's why the change was not taken. Change was taken from this point. Okay. So once enable got 1, here data was 0, then 1, then 0, 1. So you can see the change on the D out. So this is latch. So is there any question related to latch? If you have any question, please tell me. I will answer that question. Otherwise, we'll start with the flip-flop. Flip-flop is similar. There is no very big change. A small change I have to do and it will convert to the flip-flop. The same code we can write. Okay, I hope there will not be any question. So I will start with the flip-flop. If you have any question, please ask. Or I will start the new code. Okay, so I will start the new code right away. So flip-flop, I'm writing it as a FF module. As I already explained what is flip-flop, we will see this. These are simple module which I am creating. So for that, I'm writing input as clock, then reset and enable, then D in. So these are the inputs for my design. Okay, and output as D out. So this is output. Next and finish. So I will write this as a range. That's it. So I have to write the same code always at only I have to write here pause age POS AG age of clock or neg age reset. What does it mean? It means positive age of a clock and negative age of reset. On that, it will set the input. Here you don't have to write each and every thing. Here you are saying this reset is asynchronous reset. Okay, this is a asynchronous reset. Pause age of a clock, so the flip flop will trigger on the positive age of a clock, and it will get triggered, or the reset will trigger at the negative age. Okay, so of the reset, so that means active low reset. So I will write if reset, then D out equals to 1 dash B 0, else if enable, then, or I can directly write D out is equal to D in, then in. This is simple code. I will give 5 minutes time to write this code. If there is a mistake or something, you can check from this. See this. You may check multiple signal flip-flops from this. So I'm writing currently a positive edge triggered flip-flop. So you can write only pause edge clock begin range is equal to signal. Simple. Or asynchronous high, I'm writing this code. Pause edge of a reset and else begin whatever the signal is. If I wanted to write, see, I am selecting this asynchronous active low, active high reset or something you can add consistently here. So enable, if you do not want to add clock enable, so here I have added the clock enable. So pause age of clock, neg age of reset. If not of reset, 1 dash B and else if, you can write if clock enable begin range. That's it. It is that simple. You may try. Okay. Please check this. And we'll synthesize it. Let's synthesize. Make it as a set as top module. If you are not able to write the code, please use this utility, language template. There is an error. Okay. There is an incompatibility, as I said, yeah, because I have written neg age reset and I have used reset. Okay, now it will work. Now we are going to take a small break after this. After I will take counter and then we'll take break. So flip-flop, you can see clock, D in, enable, reset, one flip-flop got created. So it's a FDC, previously it was a latch. Technology schematic, you can see the same technology schematic. So here, technology schematic, one flip-flop is taken and design synthesis. One slice, 4 input LUTs, one. It has taken LUT, not flop. Actually, it should take a flop. Why it has taken a, okay, it has created a, okay. It should take one flop. Yes, one flop is taken here. You can see utilizations in IOV flip-flop one. So FDC is created. One lookup table is. This is simple. I hope everyone understood this. Now create a simulation for it. Anybody is having any question? If you have any question, please tell me. If you got any question related to it, please tell me. Okay. Okay, now I will write a test bench for it. New source, Verilog test fixture. I will write FF test. Next, FF, next, finish. You have to write the same test bench which you have written for the latch. Only you have to check the difference between what is the change between the output. The test bench, technically there is no difference. It is the same thing which I have used. Nothing has been changed. See this, nothing changed. It's similar. Everything is similar. I'm changing data at 25 and always, and I'm changing enable at 17. Enable is equal to not of enable after 17, and D in is changing at 25. I can make it 23, and reset will be made 1. Okay. So check this now. Simulation. I'm used the same kind of a test bench. There is no big change I have made. Enable is switched on and off in between, and I'm checking the result. The extra enable is there. You can see this. The clock is changing. See this clock. Whenever enable is 1 and I'm getting a positive edge, this DIN getting transferred to the output. So up to this point, nothing has been changed because reset was on. Reset is down here. So after this, it is checking enable. Whenever the enable is 1, that data is passed to the output. So this data didn't change up to this point. Reason being, enable was down up to this point. Once the enable is 1, on the edge of the clock, data is changed. See this. Again here, data is changed. So this is flop. Simple. Is there any question? Shall I finish this simulation? And the last thing we have to write is a counter after this. And then we'll take a break. And in the next session, I will start Wallace stream multiplier. I want one suggestion. Shall I allow students in the meet for Wallace stream multiplier? Or they will watch on the stream? Anybody can tell me? Okay. Okay, this part is done. So we are finished with the latch flip-flop. And then we'll start with the last part for today's first session. This is the last part. Yash, are you able to hold the stream for half an hour after this program? Just pause. Yeah. After this program, counter program, you may stop the stream. Okay. Uh, after this program, you may pause the stream. We will start after 12:30 again. I will take 15 minutes to finish this program and we'll restart at 12:45. Okay. Yeah. Okay. Yeah. Yes, 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 yes. Okay, okay, okay. So now am I audible to everyone? Actually, there was a error which I was finding. There was comma missing. That's why all the problems were coming. Now everything is done. Okay, you can see this is a counter which will be having clock, reset, and up down. Here we are using different type of assignments. We will talk about these assignments later. I'm not using a equal sign. I'm using these assignments. These are called as a non-blocking assignments. So what are these non-blocking assignments? What are blocking assignments? We'll talk about it later. Right now we have used non-blocking assignments, and you can see this is a counter which I have made. You can see this is flip-flops, and this is the summary report. So total number of slices 4, as the slice flip-flops 4 and input LUT is 4. So total 4 lookup tables are four flip-flops are used, as we are creating a 4-bit counter. Okay, so due to the 4-bit counter, it has used 4 flip-flops. So you can see here. These are the 4 flip-flops. FDC, wherever you are finding 1, 2, 3, 4, and these are the lookup tables used. Yeah. So this is all about counter. You may write the test bench in the same way which we have written earlier. So it will count from 1 to 4, 1 to 15. Simple test bench. You may, or I will write in 2 minutes and I will finish. Very quickly, I will finish it. New source. I will write Verilog fixture for counter PB. Next. Nothing has been changed. A same kind of test bench I am writing. You may modify test bench the way you want it to modify. So this is simple. If I am making this as a reset is equal to 0, and this will be 1, as I am using a pause edge of a reset. Okay, you can see here it is a pause edge of a reset. So that's why I'm making now 1, and all other blocks will remain the same. Always here already I have written the code for flip-flop test. I will copy the same code and modify it. Nothing has been changed here. Only thing is that after clock there will be here, there will be up down. Up down. This is not needed. There is no data. Okay, this is simulated. Let's see what happens. Is it counting or not? We'll see. If it is counting, then our simulation is done. Let me check this. Something wrong. I have simulated. I have to simulate this counter TV. Mistakenly, I have simulated flip-flop test. So now I'm simulating a counter. Hopefully it will work. Is there any error? Yes, there is error. Error near reset because semicolon is missing. So I have removed the semicolon and simulating the behavioral model. Check this. You can see this. So data is getting changed after reset got 0. After 100 nanosecond, data reset got 0 and data is changing. I'm changing it to unsigned decimal. Now you can see 1, 2, 3, 4, 5, 6, 7, 8. You can see it is changing in a different time. Reason being the enable is set in that way. If I make enable to set properly, it will change with say, similar time. Right now the enable is changing at a different time. So that's why the results will be like that. Okay. You can see this. So this is a counter. So if anybody is having any question, please ask or I will stop the session. So our first session is over. Is there any question? Please tell me. Okay. Okay, Yash, session into 3 minutes. So in this session, we'll learn Wallace tree multiplier and how it works. Gaurav sir, are you there? Okay, we'll wait up to 12:40, 12:55, and then I will start the session. Okay, is my screen visible? Please tell me if my screen is visible. Is my screen visible? So, yeah. So I will start the session. Actually, I have to log out and log in again, track the attendance. Need some time for that. Not able to record the attendance. Okay, anyways. Yes, do you have any extension to track the attendance? Okay, I'm starting the session. So now we will talk about the Wallace tree multiplier. Let's talk about Wallace tree multiplier. So to explain the Wallace tree multiplier, I will use this for Wallace tree multiplier. I will use this Excel sheet, basically Google sheet. So what we generally do is in Wallace tree multiplier, I will explain. Then we'll talk about how to program the Wallace tree multiplier. So the steps will be very simple. Only thing is that the Wallace tree multiplier is a very tedious program. It doesn't happen very quickly. We need time to do a Wallace tree multiplication. Okay. So in the meantime, we will see how to do the Wallace tree multiplication. Okay. So the thing is that for Wallace tree multiplication, what I have to do is first I will consider this as a multiplier, and so this is multiplicand. We are going to design 8 by 8 Wallace tree multiplication, and this is multiplier. It will be very easy to explain using this. That's why I'm explaining it using a Excel sheet first. I can explain it using a PPT also, but this will be very easy to program. You will understand why I'm saying this later. So I'm using keywords like mu0, mu1 for multiplicand. Okay. So I'm having 8-bit multiplicand. So I will mark it as a 8-bit multiplicand. Okay, this is the 8-bit multiplicand. We'll mark it like this. Okay, so I will cut it, and because later we need this space when we extend the multiplier. At that time we need this space. Okay, so look at this. For multiplier I am using m0, m1. So general multiplication, the same, we are going to do the same kind of calculations, but the calculation when we do the final calculation, those will be done little bit different way. So I am putting this as a multiplication. So I wanted to do this multiplication. So whatever partial products will be generated, so total number of partial products will be generated will be this. Total partial products generated in this case will be 8 by 8 is equal to 64. So total 64 partial products will be generated in this case. Total number of partial products will be generated in this case will be 64. So how the partial products will look, I will give the word PP0, PP1 like this for the partial product. I am using this keyword. So PP0, 1, 2, 3, 4, 5, 6, 7. So 7 will be the partial products generated. Okay, in the first case. Then, and output will be product. product size will be 8 plus 8 is equal to 16 because this is 8 bit. Okay. So this is 8 bit. This is 8 bit. So total is 16 bit. So output will be maximum 16 bit. So we need input 8 bit, inputs 8 bit and output 16 bit. That many ports we required on the multiplier. That's it. Now our output. So now when I multiply by M0, the result will be P0 to P7. See, what I mean to say here is M0 multiplied by MU0, M0 multiplied by MU1, M0 multiplied by MU2. So here something like this. PP0 is equal to M0 and basically ANDing I'm doing MU0. Okay. Then PP1 is equal to M0 and M1. Then in the same way, PP7 is equal to M0 and MU7. Okay, so it will be like that. So that we are trying to generate. So now, after that, when I start multiplying with M1, I have to leave one space on the right hand side. So I will write here PP8 to PP9. So that many partial products I am generating. So watch this. Why I'm writing like this, you will come to know very quickly when I finish my code. It will take a lot of time to finish the code. It is not very easily done. It will take at least 2 hours to finish the code because I have to explain also. So PP0 to PP6 to PP23, then PP24, PP25. Now here, what is happening? PP2425 means M3 multiplied by M0, M3 multiplied by MU1. So here PP8 to PP15 is nothing but M1 and MUN. That means MUN. I will write N because N means N is equal to 0. N is equal to 0 to 7 like this. The same way PP16 is equal to PP16, this PP16 to PP. See, this is very important to understand what I am doing because once you understand this, the code is very simple. But this is very important to understand. M2 MUN. Here this N is nothing but this value. Okay, MUN 0 to 7. So that means MU0, MU1, MU2, MU3, MU4, MU7. So I'm basically doing a multiplication and doing the same kind of thing. So you understood what I hope everyone understood what I am doing. So now here PP32, PP33. So it's not very difficult to do all these kind of things. Only thing is that it requires little more focus. Nothing else. A complete combinational design. So nothing very difficult and nothing very complicated thing we have to do. These are simple complicated things which we have to do. Okay, PP 40 41. What happened? Okay, PP right. Yeah, so PP 40 41 to 48. So 1, 2, 3, 4, 5, 6. Now PP 48, PP 49, and this will be last one after this. PP 56, PP 57. So that many partial products has been generated. 63 up to. So you can see we have created the number of partial products we needed. Whatever number of partial products we needed, we have created. So these many partial products will be there. I hope up to this point everyone is clear about what we are doing. Okay. I hope everyone understood what I am doing. If you have any question, please ask. So I have created the partial product generation. Now, generally what we do is, these are nothing but the partial products done using the AND gate. What we do is, we create AND gates like this, full adders like this. Here, one full adder is created like this, then second full adder is created. So these full adders will be added together, and then calculation is done. Array multiplication, everyone knows. There is an array multiplication kind of thing which you can do. Instead of array multiplication, what we are going to do here is, in Wallace tree multiplication, this array multiplication is done parallelly. So here array multiplication is done parallelly. See this. Now I make a group of 3, each group of 3. Okay. So what we exactly do in the Verilog coding is that we make a group of 3 adders, and these are the group of 3 adders here. These 3 partial products are added together. Then on the same time parallelly, these 3 partial products are added together, and then whatever answer comes, those will be added with this. So everything happens parallelly. In general array multiplication, first this calculation is done, this is sent here, ripple carry adders are created. Here ripple carry adders are not created, all the adders will be parallel, and all those adders will be added together. Now our first task is, we have to create this calculation. So first we will try to generate these many partial products, and we will start the coding right now. So let's start the coding. So first task is to write a code for the Wallace tree multiplier. So now I will create a new project for the Wallace tree multiplier. Okay. So I will take a new project, file, new project. I will create a new project, a fresh project, where I will create my Wallace tree multiplier. As I'm creating a new design, I'm taking a new fresh project. Up till now, I was using very simple project. So that's why I have not used the Wallace tree multiplier, but I will, new project. Now I will use the new project. So this is a project directory where I'm creating a new project. So I will make a new project called Wallace tree. Wallace tree. Just a minute, I'm creating a project. So Wallace tree multiplier I'm creating. I'm giving name it as a Wallace 8x8 multiplier. Next. Okay. So I'm making it as 3A, 358, TQG 144, same. I'm using code as a Verilog. So now this new project is created. Okay. Sorry, I have not recorded the session. So I will start the recording, the most important thing we have to do. Okay, I have started the recording. Okay, so what we are doing is a Wallace tree multiplier. In this Wallace tree multiplier, we have used this simple technique, that is MU0 to M0 to MU7. So these will be the multiplicants, then these will be the multipliers. Multiplicand will be 8-bit, multipliers will be 8-bit. Now we have to create a partial product. So these many partial products I have created, that is PP0 to PP63. PP0 means M0 multiplied by MU0, M0 multiplied by MU0. PP1 is M0 multiplied by PP1 means M1 multiplied by MU0 to MU7. In the same way, PP7, sorry, PP1 is M0 multiplied by M0 multiplied by MU1. Then P7 is PP7 is M0 multiplied by MU7. In the same way, PP8 to PP15, PP8 to PP15, that will be generated using M1 multiplied by MUN. N is nothing but 0 to 7. Same 26 to 23 will be created, where M2 multiplied by MU0 to MU7. So here N is equal to 0 to 7. Total 64 partial products, and the product length will be 64. So answer will be 64. Now we have to do a Wallace tree multiplier, where we take a group of 3 parallelly and add. Array multiplier, we create a ripple carry adder. Here we do not create a ripple carry adder. Ripple carry adder will be created at the end only. For that, I have created a new project called as a Wallace tree multiplier. So this is our project. Now I will add my first file. So new source, I will make a new module. I will give this name Wallace underscore 8x8 mult. Next, give input as mu0, sorry, mu comma m. Okay. Okay, so this is mu and m. M is our multiplier. Mu is a multiplicand and m is a multiplier, or I can write multiplier directly. And I will write here multiplicand. So for understanding purpose, I have used there mu and m, and the input size is 8x 8 to 0. Okay, and product. Answer is product. Product is basically output, which is 64, 16-bit. So 15 down to 0. Next, finish. So I have created a basic structure for the Wallace tree multiplier now. Okay. Okay, now please finish this. I will wait for 2 minutes if you want to finish it. Quickly finish it. I will wait for 2 minutes. We already know how to create a program. Now our first task is to create these partial products. So to create a partial product, I will use the generic statement. Okay, we already programmed a generic statement. So how to take a generic statement? Go to the template library. If you are not able to program, then use this. go to the generate, and here you will be able to take generic instance, generic multiple instances. I wanted generic multiple instances. So the one way is you can write 64 lines, like for pp1 is equal to m1 and mu1. So you can write something like this. So you can write here, I can declare one signal wire 63 down to 0 pp6. I have declared one signal. If you want, you can create a parameter also, and from parameter you may do the calculation. But Wallace tree multiplier generic structure cannot be written because the structure cannot be a generic. In case of a Wallace tree multiplier, you have to do multiple calculations also with that. You can create a generic multiplier, but quite complications you have to maintain. So one thing you can do is, only for handling purpose, you can create a multiplicand and multipliers width using a parameter which you can handle very easily. So multiplier and multiplicand, I'm adding a parameter just for the sake of making these things little bit easy. So I'm using it width is equal to 8. So you can write something like this here, width minus 1 down to 0, and this is width star 2 is to 0, or whatever is the size of the multiplier and multiplicand that can be used. Okay, so this is how you can write multiplier and multiplicand product. So now I am creating a product. Before that, I have to write here width multiplied by or width power of 2 minus 1. So that means 64 I have to create. So I'm writing it as minus 1 down to 0. So this is it. So I have created a wire which will be of size 64. I wanted to design a Wallace tree multiplier. So for that, I have to create 64 partial products. Look at this. These many partial products I have to create. So for that, I have created a wire 63 down to 0. Width is 8. So this will be 8 to the power 2 is 63 down to 0, pp6. So that much width I have created. Now how to write a code for that? So for that, I am using a generic statement. In the generic statement, I will go to the synthesis and coding, and I can use generate multiple statements, and simply I can copy. But here I need a nested generate. So I will copy a nested generate statement. Watch this now. So this is a nested generate. I can use a genvar, which is a generic variable j comma k. Two variables I have created. I wanted to use a nested generate. So for j is equal to 0, j smaller than width, whatever is the width. So you can use this kind of coding for any multiplier, at least up to the partial product generation. It will work very easily. So I will write here loop 1 outer loop, or I can write outer loop. This is outer loop and this is inner loop. Here I can write k, then this is k is smaller than width, then k, and this is k plus 1. So what code I have to write here? I have to do a simple assignment. Assign what I have to create? Simple. pp sig. इसका इंडेक्स क्या लिखना है हम लोग डिस्कस करते हैं, बट सिंपल फर्स्ट आई विल राइट अ स्टेटमेंट. व्हाट आई हैव टू राइट? मल्टीप्लायर I, sorry, K and multiplicand sorry, multiplier J and multiplicand K. So that means each multiplier's bit will be multiplied by each multiplicand's bit. So that's why inner loop I am putting multiplicand K and outer loop I am putting multiplier J. So I am using outer loops parameter for multiplier, and for multiplicand I am using internal one. So that means J0 multiplied by, so multiplier 0 will be multiplied with multiplier 0 to 7. The multiplicand 0 to 7. Then multiplier 1 will be multiplied by multiplicand 0 to 7. Multiplier 2 will be multiplied by multiplicand 0 to 7. Now the thing is that we wanted to put these values in the ppsig from 0 to 63. So how to do it? To do this, follow this formula. See this. What is it? I have to multiply. So each width is 8. 8 multiplied by j plus k. This is the output. 8 multiplied by j. J. Sorry. I will write something like this. You will understand. Okay. Okay. So it should be 8 star j plus k. How it works? See this. Evaluation देखो इसका कैसा है. So if j is equal to 0, what happens? If j is equal to 0 above string, how it works? J is equal to 0. So that means 8 into 0 is 0. So it will be 0 plus k. 0 plus k. K is nothing but we are changing from 0 to 7. K is equal to our internal loop, which is changing from 0 to 7. So that means 0, 1, 2, 3, 4, 5, 6 tak jayega. When j becomes 1, j becomes 1. What happens here? 8 plus k. So this will go from 8 plus 0, then 8 plus 1, something like this. So it will be 8, 9, 10, 11, 12, 13, 14, 15 tak jayega. Then when j is equal to 8, in the same way, if it comes as j is equal to, last value will be 7, 56. See, 8 into 7, 56. So 56 plus 7, 63. So here 0 to 7 it is creating. See here 0 plus 0 comma 1 comma 2 comma 3 up to 7. So 0 to 7, pp 0 to 7 will be created by this. pp 8 to 15 will be created by this. So this formula will work. So in the index you may put 8 star j plus k. Is it clear to everyone? That's it. इतना ही syntax है. That much syntax is required. No more syntax is required. It will work. So is it clear to everyone? If you find any query related to it, please tell me. Do you have any query for this? If you have any query, please tell me. Any query? Anybody is having any query? That's it. We have created the 64 partially generated products. Anybody is having any query?
So that input is 7 down to 0 or 8 down to 0?
It is a 7 down to 0 because it is width minus 1.
But you
So
are
8
writing.
minus 1, 7 down to 0.
Okay.
So when I write multiplied by 8, so 8 multiplied by 0 is 0. 0 plus 0 to 7 shift hoga.
Okay.
So when it will go to the next row, 8 multiplied by 1 is 8 to 15. So that's why I'm multiplying by 8. So our offset is basically 8
Okay, sir.
for calculation. Okay, finish this code. I will wait for 5 minutes and then we'll go to the next part. Everyone should finish this code. So that's it. This much code is required. Otherwise, what you have to do is, if you don't write a generate statement, then you have to write each and every statement particularly like this. That means you have to write something like this. Then assign pp60 is equal to multiplier 0 and multiplicand 0. Then you have to copy this statement 64 times and 0 multiplied by 1, 0 multiplied by 2, 3, 4, 5, 6, 7, then 1 multiplied by 0, 2, 3, 4, 5, 6, 7. You have to write like this. So that will take a lot of time. So instead of that, use a generate statement and your programming will be reduced. So people find it very difficult, like this kind of structure, just because they don't know how to handle the generate statement. So generic programming is the crux of all HDL coding techniques. You have to understand how to do a generic coding technique, and the solution is this. Okay, are you all done with this? Shall we move ahead? So now I have created the partial products. All the partial products are done. Only few lines of code and we are finished with the partial products. Now what we want in the hardware, half adder and a full adder. Do we have a half adder and full adder? So let's add a half adder and a full adder, because for doing the addition we need a half adder and a full adder. What we want here, we wanted to do a full adder calculation. So first what we will try to do is we will try to add these uh, three rows. Okay, so see, look at this. These are the 3 rows which we are going to handle. These 3 rows. For that I need 1 half adder and 6 full adder and 1 half adder. PP0 and PP23 will be added in the next phase because it doesn't have any other value to add. Okay, so how we add generally? Look at this. For that, what I do is generally here. Now I wanted a signal onto the addition of these partial products. So I will write S0. This PP0 will be copied as it is, S0, and carry will go into the next column. See here, when you do the half adder addition, these two, when you add these two, PP1 and PP8, the sum will be S0 and carry will go to the next block, PP2 to, we generally take a ripple carry adder and this carry will be connected to this input block. Okay, so we do these kind of things. So here we don't do this. What we do is we add this S0 and we write C0 in the next block. In the same way, when this full adder will be added, we will write S1 and carry will go into the next block. So in the same way, we will extend it. So I will extend it up to this point. See this, not this. Okay, and C0, C1 will go up to this point, and this PP23 will be calculated as it is. Now we have to do this calculation. So first, our task for the Wallace multiplier is to finish this part. Okay, I have to finish this part. Okay, I have to finish this part. For that, I need full adder. When I am adding 3-bit, I need full adder. When I am adding 2-bit, I need half adder. So let's create a half adder and full adder. So already half adder and full adders are with us because we have created half adders previously. Full adder we already created. Half adder you may not be having, so you may take a half adder and full adder. Okay. So I have added a half adder and a full adder in the design. So this is my full adder. You may create if you have not, if you are not having a full adder. Half adder, same way. So I'm keeping all the inputs same, A in, B in, sum, carry. Then in the same way for full adder, A in, B in, sum, carry. A in, B in, C in, sum, carry. Same. Only thing is that full adder will be having 3 inputs, half adder will be having 2 inputs, and that there is a change in the equation. But if you create a full adder, the same can be used for a half adder, and half adder will be very easy. A in, XOR B in, and A in and B in. That is for carry. A in, B in will be the 2 inputs. That's it. Now we wanted to call this into our multiplier. So if you have any question up to this point, please tell me. I'll explain that. If you have any question, please tell me. Anybody is having any question related to this? Simply you have to do the calculation. If you find any problem with this, please tell me. If you have not understood anything, then tell me. So that's why I'm using this Excel sheet. It will be very helpful, Google Sheet, to handle these kind of things. Okay, so now we will write a code. So first I wanted to call a half adder. Half, I will write here, half adder. So I am writing code for this part. So first I wanted to add these two, which will create S0 and C0 as an output. So for that I have to declare a wire. So wire, I don't know the width and how much S0 and C0 is required. So right now I will take a maximum value. We will later decide how much it is required. Okay, 30 is to 0, S comma C. These will be the two out inputs which we can take. Okay, so S comma C. Now let's see what we can do. So I will create something label like this. I generally use something like this level 1. L1 is a level 1. So first I'm adding all the adders at the level 1. Level 1, stage 1. For understanding purpose, how I divide the circuit, I will tell you. I call this as a level 1. These two, when I add, I call it as a stage 2. So once this is finished, this will, the result whatever you get is a level 2. Iska jo result aayega, that will be level 3, and the last one will be the product. So that is how we are going to code. So if you take a 16 by 16 multiplier, this partial products, number of partial products will be 256, and these rows will be 16. So this calculation will be very large. So generally for a Wallace tree multiplier, you get a speed up, but the problem is that it takes a lot of time to calculate. It takes a lot of time to program, because the programming is very lengthy, not very difficult, but it is very lengthy programming. Okay, so I'm taking HA11 and I'm applying input as, see this input, what are the inputs for this? PP1 and PP8. Output is S0, C0, PP1 and PP8. So I will write here, let's write here, PP1, comma, PP, I'm writing PP sig. So here I will write PP sig 1, PP sig 8, comma, S0, comma, C0. Okay, so this is half adder. Then I have to, now what I have to do? See this. Now I have to add PP2, PP9, PP16, PP3, PP10, PP7, 17. So you can see PP2 to PP7 is same number of, these are the numbers which are in line. So PP9 to PP14, PP16 to PP22. So here we can use a generic, which is nothing but a ripple. This is nothing but a adder, which will be having the same kind of input. So here, instead of writing 6 different adders, I can use a generic statement which can be replicated downwards. So your program will become very easy to tackle and code. Tackle and debug. So let's see how to debug this thing, how to tackle this kind of coding, and how to make programming little simple. So let's see. So take again the same generic statement. Instead of a genvar, you have to take only this because already genvars are declared. So you may take this. You do not need what you call okay, and basically we do not need nested generate. So I will take a new code which is not for the nested generate, a simple code. Okay, I will use the same j and k because initializing here, so j is equal to 0, j smaller than, how many adders are there? Look at this, 1, 2, 3, 4, 5, 6. 6 full adders are there. So I will write here j smaller than 6. Then j is equal to j plus 1. Now remember, whenever you write a generate statement creates concurrent or a parallel adders. It doesn't create a what you call sequential adder. Sequential calculation, it doesn't create. It creates all concurrent. There is no sequence in that. Everything is parallel with generate. Okay, so this is L1. So level 1 loop L1 S1. I will give name stage 1. So again here I have to write full adder. Full adder. So I will give name FA1. Why I am giving very name very consciously, because when you debug you will have to understand in which generate there is a problem. So if you understand that, then it is very easy. So if you give a name consciously, it won't create any problem. Otherwise it will create a problem. So pp sig, we have to enter some value here. pp sig, we have to enter some value here. Then pp sig, we have to enter some value. Then some value. Instead of a sum, I will write s some value. Then c some value and semicolon. So let's see what we have to enter. So pp sig, what is it changing from? 2 to 7. So I will write here j, so 2 plus j. So that means what happens? 2 plus j means this will change from 2, 3, 4, 5, 6. 2, 3, 4, 5, 6. 7, it won't. So 2 plus 0, 2 plus 1, 2 plus 3, 2 plus 4, 2 plus 5 is 7. So 3, 4, 5, 6, 7. These many values it will take. 2 plus 0, 2 plus 1, 2 plus 2, 2 plus 3, 2 plus 4, 2 plus 5. After 5, it won't increase because it is less than 6. So it will go up to 5. So 2 plus 5 is 7. So maximum value it can go up to is a 7. Then here you can write 9 plus 7 is 9 plus 5 is 14. 16 plus 5 is 21. So here you may write 9 plus j. This is 16 plus j, and this is s. What? The number is 1 and 1. 1 and 1. 1 plus j, 1. Okay. 1 plus j, and this is 1 plus j. E1 plus j. That's it. We have coded up to this point. Up to this point, coding is done. Now I have to add one more half adder for 15 and 22. So let's add one more half adder here. So copy the topmost code again here and write here. Simple half adder. Here I will give new label HA2 of level 1, and here you have to write PPC 15 and 22. So here I will write 15. This is 22, and the result will be this 7 and 7. So I will write here S7 E7. That's it. With this small coding, we are finished with this level. Otherwise, we have to write 6 full adders, 2 half adder instantiation. So total 8 half adder instantiation you have to write. Instead of that, I have written a simple code which can be copied and pasted again and again and tested. Is it clear? All of you understood this? Please tell me. If you have any question, you may ask. It's very easy to do this calculation. It's not very difficult. If you have any question, you may ask. No problem. Okay. So I'll go to the next part. Now, I have to go for the next code now. I have coded up to this point. So now I have to add these 3 rows. So how to add these 3 rows? Let's add these 3 rows. So I will give new color to this, as this is the new color I'm using. So as these are the answer of this code, and pp23 is coming from top as it is, I will write there pp23 because we have to keep the order. So I will give this as the same color which is given to the previous one. ये दोनों का same color होगा. The color will be same for both of this, and whatever answer for this will come will get a same color. So you will understand what I am going to do and what I am adding. So now pp24 as it is, as it doesn't have anything to add. Okay, now pp25 to 32, the same kind of thing is there, so I can use the same kind of code here, only I have to change the number. Okay, so I will write here level 1 stage 2. So I am again on the level 1 stage 2. Simple coding. Here I will write HA3 L1. Now look at this ppsig 25 and 32. So I am writing here ppsig 25 32 And what will be the output? 25 and 32. So I will write here. After this, whatever is the value, I will write, extend here. So S8, C8, then S9, C9. So S8 and S9 will be extended up to this point. Okay. So these are the area of concern for us right now. So we are talking about this now. And this PP47 will be taken as it is. PP47. I will fill this with a white color. Here I will fill this with a white color as this is as it is taken down. Okay. So watch this. Now I have to create this. So I will write SC8 as output. So here I have to write S8 C8. The same function will work. I don't have to do anything. Only thing is that I have to make it S2 loop change. This is H4. So how many adders I am using, you will be able to calculate just looking at the code. So in that, from 26 to 31, 30, 26, 33, 40, that I have to change only. So I will make here 26, 33, and 40. So how much it will calculate? 26 plus 5, 31. 33 plus 5, 38. 40 plus 5, 45. Let's see. 26 plus 5, 31. 33 plus 5, 38. 40 plus 5, 45. 39 and 46. Next, half adder. So this will be 39 and 46. Here, outputs. What are the outputs? 9 to 14, 9 to 14. Okay. So I will write here. You can see the previous also. So from that also you will be able to find out. Here 8 hai, so that means here it will come as 9 plus 5, 9 plus 5, and this will be 9 plus 5 is 14. That means this is 15. This is simple. See this. This is 15. Done. The second level is done. Now 2 cannot be added. The rule of Wallace multiplier is you can add 3 rows at a time. So that means 3 partial products at a time you can add. If it is not happening, then it push it to the next level. Okay. So up to this, we have finished the calculation. Now I have to copy this as it is downwards. So copy this as it is here. Just a minute. For understanding purpose, I'm putting like this. Now this is our level 1. This is called level 1. So this is our level 1. Now we want to create calculation for the level 2. So this is level 1. Okay. I can show you. This is level 1. I have finished with the level 1. Now this is level 2 calculation. So here I will again use the same kind of programming. Only thing is that I have to change the inputs little bit. See this again. Output of these two. Let's see. We have to add now these 3 rows I have to add. Up to this point I have to add. These three will be added together and these three will be added together. Watch this. These three and these three will be added together. Simple. So when we add together S2 to S7, so here I need one half adder. Here PP24 is there, so generic statement will not work. So only generic will work for 4 adders, and in next it will work for, yes, again it will work for 5 adders. 1, 2, 3, 4, 5, 6. For 6 in the next one. For first case 1, 2, 3, 4, 5. Generic will work for 5 and here for 6 because here PP24 is there. So separate instance we have to take. Okay, let's take a separate instance for that. Let's try. So now I am going to level 2 stage 1. So this is my level 2 stage 1. How to do this? Let's see. This is level 2 stage 1. First half adder. For this I am creating a half adder. Then for this I am creating a full adder. For this I am creating a generate block, and for this I am creating a full adder. So what I will do is from this point of from this time, whatever is a half adder, I will give a particular color to that, and for generic block I'm giving particular color. So this will be the generic block. This will be the full adder. Okay. Different color I will give. Okay, this will be the full adder and this will be the half adder. Okay, so this will be again the full adder. Okay, so I will write something like this. So this will be the generic block which I can use directly. The generic block is shown by this color. Sorry, the block is shown by used this color. I don't know which color I have used. Okay, I'll change that to okay. This will be the same, and this will be half adder, and this will be half adder. So we have to code like this, and these will be the full adders. That's it. Let's finish the code. So now first half adder, I have to take half adder as it is, the generic block as it is. Only one extra full adder calculation is required. So first half adder HA 5 L2, or I can write HA1 L2, and instead of PP6 I will write here. So here I will write S1 C0. So that means I am taking values S1 and C0. So write this. So two calculation I have to add. So this is S1 C0. So I have added S1 and C0. What will be the output? Output will be again, we have to continue this output. We came up to C15, so this become S16 and C16. Then S17, C17. Let's continue up to this point. S16 to S17, then C16 to S23, and these three will be copied as it is here. So these will be copied as it is. Okay, and this S0 P0 will be also copied as it is. There is no change. S0 is nothing but our P0. So now product 1 is available, product 0 is available, product 1 is available. Product 2 will be available when we calculate S16. Now this part is done. So let's start S16, C16. So right here S16, C16. Simple. Done. Now the next part. This one. 2, 1, PP24. So I want one full adder instance. So I will take one full adder instance. So I can use this instance. FA1, L2. Sorry, not here. I have to copy here. FA1, L2. So what are the inputs? I'm talking about this S2, C1, PP24. So this is S2, C1, PP6, 24. Answer is C17, S17 and C17. That's it. So we came up to this point, S17, C17. The next is generic adder 3 to 7. So 3 to 7 we have to make. So instead of 6, I will write here 5. That's it. So PP6, 3, and here I will write S, as it is S3 to S7, C2 to C6. So 2 plus 4, 6, 3 plus 4, 7, C2 to C6, S3, then C2 plus J. That will go on increasing. I have to change the loop names here. L1, S2. So that is S1. L1, this is L2, S1, stage name. Okay. C2J, PPC. Stage name you can give anything. I'm just giving particular name to understand what happens when we code. S3 to 7, C2 to 6, S8 to 12. Now, here I have to write S8 plus 4, 12, and PP6 will be 17, after that 18. This is 18, this is 18. Sorry, there is some mistake I have done. C, this is 3 to 8. 3, 2, this is 8. Done. This is also done. Now the last one, half full adder again. Instead of half adder, there will be full adder. PP23, C7, S13. So copy this full adder and remove it. Full adder, FA2, L2. And what are the numbers? 23, 7, 13. Let's write So this is 23, 7, 13. So this is PP23, say 7, S13. So I will make it PP6, S7, C13. Answer will be S23 and C23. S23, C23. So done. These parts as it is. Now the next part. So is anybody doing this? If anybody is doing, please tell me. I will wait for 5 minutes. Otherwise, I will move ahead.
Sir?
Have you understood this? Is there any question?
Yes, sir.
Yeah.
Sir, am I audible? Sir,
Yeah,
you
yeah.
have changed the instantiation name of full adder FA1 L1.
I have to change.
Yes,
I will
sir,
make it.
and above two.
I have made this. Now FA1, I will make it FA2, and this is FA3. Okay. So there will not be any problem later when I handle it, right?
Sir, in the above group too.
Above?
Sir, the in the line 57th, I guess you have not changed the name there as well.
L1S2. No, it is L1S2 anyways. There is L1S1 name over. So there will not be any problem. If there will be problem, the syntax, when syntax check will happen, we will come to know whether it is reused. It shows the error. Then we'll come to know. But see, the problem is why I'm using this technique, because the thing is that it is very tedious and will create a problem. I hope you all are understanding what I'm doing. So is there any other query? I think I used a proper name here, L1S2. So there will not be any problem. L2S1 I have created here. So I think it will work. So now we will move to the level 2, page 2. Let's start. So now I am coming to this part, the last part. After that, I have to just do two more calculation and done. Most of the calculation will be done after this. So again, I have to write here C8 as it is. C8 as it is. I'm copying. And here I will write S24, then C24. S24, C24. This is S25, C25. So 24, 25 will go up to this point, and this will go up to this point. So obviously the range went above 30. So first thing we will do is we will change the range of this to 50, because we don't know how many wires required. We will make this change whenever needed. So it will just keep track what we are doing here. And I'm copying this PP63 as it is downward later for the later use. Okay, here PP47 copied as it is. So here I'm copying PP63, Control B. That's it. So watch this now. So let's use the same kind of coding. Here you need 1/2 adder, 6 generate, and 1/2 adder. So the block used here can be used here again as it is. There will not be any problem. Very easily we can copy paste. Just we have to change the label names. So why we change the label name and why we are giving name like that? You can give any name. Only thing is that it will be very easy to understand and will remain in our mind what we are trying to program. Okay, so HA1, L2, so this is HA. Just a minute, someone is trying to enter. Admit. Okay. Okay, if you have any question, please ask. There will not be any problem. I hope. HA2, L2. I'm using HA2, L2, FA1, L2, FA2, L2, FA3, L2. So this will be FA4, L2, and this will be HA3, L2. Will be L2. That's it. Only now I have to give the names. What are the names? 948. Let's give the name. But what is 948? S and PP48. Okay. S 9 PP48 and S is what? Answer is 2424. So this is 24 24. You can keep track. 23 is there. Now I'm getting 24. So J is equal to 0 to 6, J plus 1. Now here I am using L1 S1. Instead of that, I will use L2 S2 loop. Level 2 stage loop 2 stage 2. Okay. FA12. Now I have to give new names here again. So the names will be C2, C15, and PP names will be similar. Only first name I have to change. So C2. So the name will be C10 to C15. So C10 plus 5 is 15, and the remaining will be PP 49 to 54, 56 to 61. So 49 and 56. Here I will write 49 and this is 56. The answer will be here 25 to 30. 25 to 30. So I will write here 25 to 30, 25 to 30. That's it. Done. And the last half adder. I have to take this half adder. 55, 62, which will give 31, 31. So 55, 62, which will give 30. What is it? 31, 31. No? 55, 62, 31, 31. 31, 31. Done. 55, 62, 31, 31. Is there any question? If anybody is having any question, now we are coming to the last stage. After this, we will get the answer. We are coming to the last stage. Most of the answers already are available with us. We already got product terms, these 3 product terms. So if anybody is having any question, please ask. If you want to ask any question, please tell me quickly. Okay, I'll continue then. Okay, so now we are going to level 3, stage 3. Level 3 stage 1. Okay. So here what we need. Okay. So these two will be half adders, which we wanted to add. So this will be half adders. Then we are basically adding this part. Now 3. These 3 we are talking about. We are interested in this part. So 19 to 23, 18 to 22, 8, 24 to 27. So we need one full adder. This will be a full adder. Let's take this as a full adder. Sorry. This as a full adder. And this will be our generic loop. This will be generic loop. Which color I am using? I'm also not. I hope this will be the color. Okay, this will be the color. So this is I'm using, and the last one will be again a full adder. So use this full adder. Here you need 2 half adders for this. Again 2 half adders. So that's it. Once you do this, there will be only one stage remaining, which will be a ripple carry adder. There is no solution. At that point, you have to use only the ripple carry adder. As it is, that will be connected. So here, let's take the answers and find out what we can do with the last part. This we will use directly in the next loop. So we came up to what? 31. Up to 31, we have counted as 31. Where is C31? Is there any mistake I have done? Okay, C31 is on the lower side. Okay, C31 to up to C31 we came. So this will be S32 and C32. So this will be S33 and C33. Let's take it. What point? To this point, and this will be up to this point. That's it. Done. So most of the coding part is done once we finish this part, and the only last thing we have to do is the ripple carry adders. So we have to add multiple ripple carry adders after that, and the final code will be done. We will get the products. So we will copy PP0 as it is here. These 3 we have already calculated here. I'm taking this here directly. Sorry, here as it is. There is no use for this because these are already calculated. Only part I have to calculate is this. So let's calculate. So first I need 2 half adder. Let's start with 2 half adders. Half adder. HA1, L3, HA2, L3. So what is the input required? S17, 18, C7, 16, 17. S17, S18, C, and this is C. 16, 17, and the final answer is 32, 32, 32, 33. So this is 32, this is 33, C 32 and this is 33. So these codes done. This part is done. Now I'm talking about this 1918 C8 S19 C18 C8. So I need one full adder. I'll take full adder like this. Let's do it. So this is full adder and I will give this name F1 L3. So level 3 we are talking about. This is S. What are the numbers? S19 C18 8. S19 C18 C8 and these will be 34 and this will be 34. Like this 34 34. We came up to this point. Now we have a generic block. So copy here. Now we have to make index to 4. So take this generic block again. Copy here. Make it to 4. And the numbers will be S20 to 23. So S20, 20 plus 3, 23. Then next number is C19 to 22. So I will make it as C19 to 22. The last number is again S24 to 27. S24 to 27 and I will make this as FA2 L3 L3 S1 stage. And the last point. This is done and I'm going to now add these 4s. So output is 35 to 38. So mark it as 35 and this is done. So this part is done. The last part is remaining. So this part is also done. So we finished up to this point. Now I want one full adder and 2 half adders. Again, the same thing. The top part we will copy again. This one full adder and 2 half adder required. I'm copying it here. The thing is that full adder first required. I will mark it here. So FA1, FA2, this is FA3, HA3, and this is HA4. That's it. Now first S14, C23 to S28. S14, C23, S28. S14, C23, S28. Answer is 39, 39. So this is 39, 39. Then the last one, 15 and 29. S15, S29. S15, S29. As I said, this coding will be tedious, but it will be very easy to do. 28 and 41. Answer will be 40, 40. Sorry. Answer will be 40, 40. This will be 40. This will be 40. This will be 41. And this will be 41. The last code. This part is remaining. 47 and 30. PP 47. So here I have to write PP sig 47 and the last one is plus 30. So this stage is also done. So we finished coding up to this stage. This coding is also done. Only last part is remaining. I have to copy as it is here. This part I will copy here. So it will be added together. That's it. Done. So this is our product now, the last part. Only one adder and the answer will be. See, you can't now take again the 3 and then come to 2. That will not happen. Here you can directly go for the last ripple carry adder. So here you can write PR0, that is product 0, PR1, PR2, what you can write PR, what happened, PR01, PR2, what happened, is there any difference? Yeah, there is a difference. PR14 and one more will be there, PR15, carry from this. That's it, 16-bit calculation exactly. So this is last part of our calculation. Anybody is having any query? Have you all understood what I have done? This is last part of the calculation. And in 10 minutes, we'll finish the Wallace tree multiplier. If anybody is having any query, please tell me. Simple calculation is required. Last part is remaining. Okay, done. Okay. Then we'll try to synthesize this after that. Probably there will be multiple errors and then we have to solve all these errors step by step. You may do one thing. After each stage, you may synthesize and check. I have not checked, which actually I have to, but I haven't checked. So I am writing directly and checking. So level 4, stage 1. So the last thing I'm going to program. So I will program like this now. PP0 will be marked to product 1. So I will write sign product 0 is equal to PP with 0. Sign product 1 is equal to S0. Is not used anywhere. Then assign product 2, second bit of the product will be assigned to what is there, S16. So right here S16. Done. Now only few adders we have to write and our code is done. So now S32 is also P3. So I will write S32 as P3. So P3 is S32. Then I have to write 2 half adders and the carry will be given to the next. So 33, 34, 35, 32, 33, 34. Directly I can use as a generic block. So here I can use a generic block. So use it as a generic block. Let's use it as a generic block. 24 to 29, 36 to 41, 35 to 40, 30, 31, 40. ये भी चलेगा. Up to this point, there will be another generic block, full adder generic block. Okay, so this is full adder generic block. This will be full adder generic block. Okay, this will be full adder generic block, and this will be half adder generic block. So these will be generic blocks. But I'm using a different color, so I will do better with color that color. But that's a generic block. This is again generic block. Only thing is that half adder and full adder will be used. Okay, let's do it. So 2 generic blocks required. I will copy 2 generic blocks from the top, and that's it. Very easy coding will be done, and we will be finished with the coding. Let's do it. Yeah. Okay. Yeah. 10 minutes only, and that's it. After 10 minutes finish, you may stop streaming after 10 minutes. There will not be any problem. Then I will upload the recording also. Most of the code is done already, actually. There is nothing remaining now. Okay. There will be 2 such blocks. This will be half adder block. I will remove this. I will put one half adder here. And I will make this as L4. This one. J. This is L4. FA. And how many is there? 1, 2, 3. So I will make it 3. And the last one is 1, 2, 3, 4, 5, 6, 7. 7 is there. So I will make it second as 7. That's it. So what I have to write here? S33. S33 plus J, then C32. C32 plus J and S की जगह आएगा product. Product how much? From 4 to 4, 5, 6. 4 to J. 4 plus J and C. Now here carry will be generated, but this carry will go to the next block. Here you have to remember there will be a carry which will be directly added here. So probably one more calculation is required because one more carry will be generated, right? Yeah, one more calculation is required actually. Here it will work, but the next block for it will not work. So we can't write actually. Here up to this point it will work. After that it won't work. So that's why we have to mark it later. So we will mark something like this. One more calculation is required actually. Yeah. So I will mark it as S41, C41. So S42, C42, S43, C43. There is no way out because there will be 4th carry generated which cannot be accommodated by the last block. So that's why we can't do anything. S50, whatever is the answer, that will be there. Yeah. Mostly there will not be carry from this block, but we have to just calculate. Okay. One more step is later required. So I will mark it as, instead of product, I will write S42, C42. S42, C42 plus J. That's it. And the last one, 027L4 FA2. So here I have to add these 24 to 30. So I will mark it as C24. Then next is S36, S36, and the last one is S36 and C35. C35 plus J. That's it. C35. So we will get S45 and C45. S45 and C45. 45 plus 6. Up to this, it will calculate. The last one I have to add again, half adder. One more half adder is required, that I will calculate. Take this as a half adder. Adder HA4, L3, and this will be HA1, L4. This will be FA1, L4. This will be HA2, L4. And the last calculation is C31, PP63. C31, PP63, and this will be last 52, C52. S52 and C52. Done. Now the last one, only half adder is remaining, which can be directly calculated. So this part up to we have already calculated. S42 we can write here directly. The last point, level 5. So 5 level of coding is required in this 8x8 multiplier. Level 5, stage 1. Only one stage is there, level 5. Only half adders are there. You can use carry look ahead adder, any other adder which will do the calculation faster. You may try any kind of adder. So S42 first, directly I will add to assign product 4 to S42. So this is PR0123 as it is. Control C, Control V. Yes. Here there is no possibility of a carry. Mostly there will not be any carry generated. That's it. S42 PR4. So now I have to create this as a carry part. This will mostly come as 0. if I have not made any mistake. If I made any mistake, then this will create a problem later. If somewhere I have made a mistake, then it will create a problem, obviously. So S43, C42, the last part. This block I will copy again and I will write here. Product 16 most of the time will always come as 0. How many adders are there? Sorry, one full adder is required. One half adder, sorry. Up to this, there will be the, and this will be the half adder. Because whatever carry it will create, that will be generated here and added here. Okay, we'll do it. S43, C42. One half adder will be there. Half adder. The last part, in the last part, this will be the half adder which will be generating a carry, and all other will be full adder because there will be one carry which will be directly added. So I am directly creating one carry and adding here. So I am creating the last adder as a ripple carry adder instead of a parallel adder. Otherwise, this process will go on continuously. We have to finish this process at this stage only. So that's why whatever carry will be generated, that will be added here, and I will use that as a input carry for all these blocks. Okay, so here only carry will be generated, sum will be product answers. So S43 and C42. So I will write here S43, sorry, here S43 and C42. This will be S43, C42. Answer will be product 5 and C53. Now here I'm coming to level 5. So I need this, not half adder, I need here full adder. That's it. So generate 0 to 7. How many? 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 full adder and one half adder later. 9 full adders. So I will write here 9. 9 full adders. And this will be FA1 L 5. This will be 5 HA1 L5, and we will write last thing S44 C43. Yes. Yes. Pull down. Just give information there in the chat box. Because the last part is only remaining, that I am finishing. Yeah. S44 C43. 43, and the last part is whatever carry generated will be